Good afternoon, Mario. Thanks a lot for the talk, the wonderful talk, and also for giving us this interview. So we would like to start with maybe more personal question. What drove you to pursue a career in science, in scientific research?
That was kind of obvious for me since very early, especially once I got to the university. I was exposed more to subjects related to physics, to mathematics, and I found a lot of beauty in it. It was pretty much clear to me that I wanted to explore these things further. My problem is to know exactly what I wanted to explore more, because I liked a lot of topics.
As a follow-up question, if we look at your research, it's quite interdisciplinary, because it's kind of like the crossroads between photonics, but also condensed matter physics. But also, if we look at your CV, it's also kind of like interdisciplinary, because this thing you were discussing about electrical engineering, but also applied mathematics and then physics. So could you walk us through this process? And also, when you tackle a problem, when you approach a problem, you have many different viewpoints.
Yes, so as I was mentioning, I was attracted to different fields. One of them was also technology. That's why I majored in the electrical engineering, and I did a PhD in electrical engineering, more related to electromagnetics, to classical electromagnetics. In parallel, while I was taking my course on electrical engineering, I tried also to explore the other things. At the time, we didn't have internet, we didn't have ChatGPT, but we had libraries. So I would go to the library, and sometimes I would rent a couple of books and bring them home and try to dig on these books. So since very early, I tried to have knowledge on different topics, and it has been quite useful in my research, because indeed, even today, I try also to look at different things, and this is kind of one of the criteria how I pick the problems in which I work, is try really to explore things that I don't know. And so this is kind of how I guide my research, is mostly by curiosity.
Connecting to your talk, you discussed thermodynamic paradox, a type of thermodynamic paradox in the context of photonics. To a student, like say an undergrad student just learning Maxwell equations, the connection between electrodynamics and thermodynamics is not so obvious, but also thermodynamics seems like a set of unbreakable rules. How can there be a thermodynamics paradox in photonics?
Well, I start with the end of your question. So I think thermodynamic rules are indeed unbreakable, but however, you can have settings in photonics or in problems that correlate with photonics that can lead apparently or not to a paradox. And so the connection with thermodynamics and photonics, it comes naturally, because often when you think about optics, you think that you have a classical source or a laser or something like this, and it generates a wave that propagates. But there is other type of sources, namely because there is thermal agitation, and this also creates radiation, so it's this thermal light. And when you have a system in equilibrium, and if it's at finite temperature, the different elements of the system will be exchanging energy between each other. So if you pick an atom, it will be radiating, so sending energy to other atoms, and it's also picking energy that comes from the others. So the important thing is that the amount of energy that every given element receives should be the same as the amount of energy that it gives away, so that there is indeed this thermal equilibrium. Now, the paradox shows up because in some systems, some photonic systems that are engineered to have unusual properties, like for example, light just goes in one direction. So you kind of create a preference, and it's this directionality that can indeed lead to something that may look like a paradox, because if one element radiates, the energy is forced to go in one way, and there is sometimes not an obvious way to return it back. So this is, in such a context, it is the context that indeed we can run to situations that are a little bit different than usual.
Continuing with, because in your talk you also discuss topology, something that's also very prominent in your research. But when we think about topology, normally we think about coffee mugs, donuts. It's very basic, but that's maybe the most intuitive idea. But how can the shape of an object determine the way light propagates or behaves? What is connection between topology, shape, but photonics? How are they connected?
Well, I mean, topological ideas are not so simple to explain, and that's why people often pick up the examples from geometry, which are very intuitive, and we can kind of visualize what we mean by topological. So in the case of geometrical objects, the topology it's related to the very shape of the objects. Typically it's related to the number of holes that the object has. And in a material, we cannot visualize the number of holes. However, there is a similar concept which is related to the geometry of the band. So the materials typically have like a dispersion that controls how the wave propagates in them. And so there will be a relation between the different electromagnetic modes, and this determines the geometry. And it's an invariant, if you look at it from a mathematical point of view, that it's pretty much equivalent to the one that you see in the theory of surfaces, even though it's less obvious to explain. So the significance of this is that some physical responses depend on this invariant. This is what makes it so striking. And the first example of this in condensed matter, of this topological effects, was in the quantum Hall effect, where you have a material that is an insulator, and we all learn in solid state physics classes that an insulator is supposed to have zero conductivity because all the states are filled. And very strikingly, you find that even though all the states are filled, because of this topological thing, you can have a non-trivial conductivity that on top of everything else, it's quantized. So we are not used to responses that are quantized. Usually, if you have mass, or at least in a macroscopic scale, if you have mass, if you have density, if you have all these properties, they can vary continuously, at least if we are discussing it from the point of view of macroscopic physics. But here we have an example that is not like that. That's how it is so striking. So for photonics, we don't have this nice example of condensed matter where you have a response that is quantized. However, you can make other connections that are in some sense analogs of these. For example, again, if you look at thermolight, so light generated by fluctuations, you also find that in some topological settings, some properties of this thermolight can also be quantized. In this case, it connects with the angular momentum. And again, this quantum number, it's related to the Scher number. And so it's a quite powerful and sometimes intriguing effects. And so it's really fascinating topic.
Thanks a lot. So the last question about topology is about a concept that is ever present in topological physics, both in photonics and in solid-state physics, which is the bulkedge correspondence. Could you give us an explanation, an intuitive explanation of what this bulkedge correspondence is and why is it so important in photonics and solid-state?
Yes, so the bulkedge correspondence, maybe it's the most intuitive way of saying the impact of the non-trivial topology. It states that you can connect properties of a bulk material, which is something that you compute without knowing anything about the interface, and you can use these properties that just depend on the material to predict what happens when you form an interface with another material. And the bulkedge correspondence predicts the number of states that you're going to have there that is controlled by this topological invariance. It's the difference of the topological invariance of the two materials. And so this is very unusual because we are used to thinking that the states that you're going to generate should depend on the interface, on the way that you're going to pair the materials, on the type of materials. But no, it's something global that it is there. And so it is quite striking for this. So from a more technological point of view or from application point of view, it's also interesting because these states are unidirectional, so they just propagate in one way, and they are immune to backscattering, at least in ideal circumstances, which means that even if you deform your interface or if you put some obstacle there or something of the sort, the wave is not going to be reflected. So it just continues. And this can be quite interesting to make better waveguides and more robust to perturbations and so on. So people have been working on this a lot since this concept appeared in photonics now more than 15 years ago.
Okay, so I think we've covered the topological part of your talk, the photonics part of your talk, but we have yet to cover the heart of the thermodynamic side of your talk, which is the fluctuation dissipation theorem, which is also very present in your work. Could you explain to us what is the fluctuation dissipation theorem? Also, if there are instances in which this theorem doesn't work?
Yes, so the fluctuation dissipation theorem, it's the tool that we have to describe this thermal light, so the light that is generated because of thermal fluctuations that are there. And it allows us to predict the correlations of the fields. For example, it allows us to predict what is the thermal energy that will be stored in some cavity, for example, that is kept at some constant temperature, or it allows us to predict how the thermal light may circulate inside some cavity. Now, your question, if there are instances where the fluctuation dissipation theorem may fail. So, itself, I don't think it can fail, but the fluctuation dissipation theorem, it's built on a macroscopic theory, and every macroscopic theories, they have limitations. It's formulated in terms of properties of the materials themselves. And so, for example, in the context of my talk, I discussed one setting where in a particular description of one of these topological and non-reciprocal materials, we are led to a contradiction if we assume that the material response is in a certain form, which is like the simplest form that everyone would use. And this indicates not that the fluctuation dissipation theorem is wrong. I don't think it is wrong, it is for sure correct. It just indicates that the description of the material is incomplete and we need to consider a better description. And so this is one of the nice connections between non-reciprocity, topology, material sciences, and so it's a quite rich set of topics that are interconnected.
The next question is a little bit less scientific, so to speak. What is your favorite physical phenomenon, one that you say, I love it, and also one that you don't yet understand, that you say, it eludes me?
Well, I have many favorite physical phenomena, but I'll give you the same as my favorite, and as the one that I don't understand it. One that it's always intriguing, and of course, you when you say you don't understand it, there are different levels of don't understanding. But I like a lot the phenomenon of quantum interference. It never ceases to amaze if you think about it. For example, I could give you specifically the double slit experiment, where you have a wave that goes through the two slits, and you can form interference patterns depending if it's just one open slit or if it's the two open slits, and the records of the electrons on the screen or of the photons or whatever depends on this interference. And this, of course, it's very counterintuitive because you cannot understand it in a good way in a classical fashion, and so for me, I think this is one of interrelated effects. It's I would say it's my favorite, and it's the one I don't understand, or at least there are many aspects I don't understand. There are some aspects I understand, but there are other aspects that I still find puzzling and intriguing, and I'm not happy with the way I understand them.
So the next question is also, I guess, about the role of a scientist as a supervisor and the contact with students. How important do you think it is for a researcher or scientist to have frequent interactions with students, both at the level of teaching an undergrad or master course, and also mentoring?
I think it's good for many reasons. Well, at least in my case, I think it's important, first of all, because if you are in contact with students, but I mean, not only with students, could be also with colleagues, but it obliges to kind of distill what you know and to explain in a way that can be understandable. And so these interactions for sure are useful. And as you explain what you know to the students, or as you discuss some problem with your students, you are going yourself to understand points that maybe, or at least see different points of view, even through the interactions. Sometimes, of course, through these interactions, the students also contribute and also make you look in different directions. You can realize that some problem, maybe it's richer than you thought, because maybe you are confronted with situations that you did not think yourself. So this is one of the aspects I would say. Besides that, it's satisfying to interact with young researchers, so with students, because often, of course, they want to learn. For them, everything is new, and it's exciting also to pass the little that we know and try also to instill in them the taste for research and pass whatever we know and see them grow as researchers, as independent researchers. So.
And we would like to end this interview by asking you, what was the best advice that you ever received that helped you in your scientific or professional career, and also an advice that you never got, but that you wish you had received?
By working with some colleagues, I learned that one important thing is to learn to ask good questions. Maybe in the beginning of my career, I would choose problems not based on questions, but based sometimes on trying to solve something, or something that is more mathematical or less mathematical, something that was not evidently relevant just for the pleasure of solving. But through interactions with other colleagues, I understood that, okay, maybe instead of solving problems, you should just stop and think, what are really the good questions that you should invest your time, your finite time, to solve? And I think this is really important. And as advice that I could give to others, to find something that is worth working on and different from what other people are doing. Because if other people are already doing it, maybe you're not going to do much different, right? So you should find something original and take it until the end. And also for students often are very stressed where they are going to publish their articles. If it's going to be an high impact journal or if it's going to be less impactful or not. What is important is to do good work, and if it's good, people will notice. If it's less good, it does not make too much difference where you published in the end. So this would be my take on that.
Okay, thanks a lot, Mario.
Thank you, Jaime. It was a pleasure. Thank you.